Okay, so hello everyone. Can just anybody just write or send an emoji if my voice is coming? Is my voice clear? Okay, fine. Thank you. Okay, so let's start today's discussion. So this is basically your week number three, lecture number three of weekly numerical sessions on the subject of mechanics of solids. So in the last week, sir has basically discussed regarding, I think there were two lectures on tutorials. One was on thrust, one was on friction, and then two, three new concepts. One was regarding your force displacement relationship, then the hoop stresses and the mechanism of belt around you. So let us start the discussion directly. So I'll be going with a little bit revision first of all, and then we can start with the problems. Okay. So let's start discussion directly. So I'm Samir Lavankar. This is lecture number three of weekly numerical session for mechanics of solids. Let's start our discussion. Fine. So after the tutorials were being done, so we have actually completed majority of the concepts in the previous lecture only regarding the trusses and friction. So I won't be focusing on that. I'll be focusing on the next concepts like hoop stresses and the force displacement delta, etc., PL upon E, and the mechanism of belt, mechanism around the belt. Okay. So let's start with the first discussion, which is regarding the force displacement relationship. Okay, so basically, in this, what has Professor explained, the analysis process is broken into three fundamental steps. The first is regarding the study of forces and the equilibrium requirements. So the concepts are again same, nothing typical. You just need to understand. First of all, you need to make the free body diagram. The second thing is regarding the summation of forces, and the third thing is just addition is that you need to understand what is the deflection. One of the typical questions which are being asked regarding these concepts are regarding if some of the members are basically beam members, as in rigid members. Okay, so you need to understand that part. Otherwise, apart from that, it's correct or previous as previous discussion. Okay. The study of forces and equilibrium requirements. So this involves creating a free body diagram to understand the forces acting on the system and ensuring it satisfies the conditions of equilibrium. This is the first part in which we need to understand the study of forces and equilibrium requirements. The second is regarding the study of deformation and geometric compatibility. Okay, in which this step addresses how the system deforms, ensuring that displacements are consistent with the physical constraints of the structure. The third is regarding the application of force deformation relations, in which we connect the cause, that is applied forces, to effect deformation using the properties like the spring constant. Okay, spring constant as in K. So let's say, for example, if you are working on springs, so we use the equation directly, that is F is equal to K times delta. Okay. So this was the first concept. The second concept is regarding the uniaxial loading and the modulus of elasticity. So in linear systems, if we follow the Hooke's law, we get the modulus of elasticity, which is nothing but the slope or the ratio of stress to strain, right? So for linear elastic materials, the relationship between the applied axial force P and the deformation delta can be plotted. So let us say the professor has also plotted it regarding two different concepts. One was regarding the linear system and one was regarding the non-linear system. So let us suppose if I plot it regarding the linear system, so it may be so these are regarding three different modules having three materials having three different values of modulus of elasticity. Okay, so we can basically write this as P and this we can write it as delta. Okay, so basically if we write P upon A and this is delta upon L, so we can basically get this slope as nothing but equal to capital E. Okay, so this can be E1, this can be your E2, and this can be your E3. Fine. So these are the concepts regarding this point. Next thing is your so for linear elastic materials, the relationship between the applied axial force P and deformation delta can be plotted. So when normalized, these plots converge leading to the definition of modulus of elasticity E, representing the slope of the stress strain line. This leads to the fundamental formula for deformation of uniaxial member, which is nothing but delta is equal to PL upon A. Okay. So this is how we get the first formula. It is nothing but delta is equal to PL upon A. Okay. Next thing is regarding when P is the force, L is the length, and A is the cross-sectional area, and E is the modulus of elasticity. Okay, so I have already explained what is modulus of elasticity. Modulus of elasticity is nothing but the ratio of stress to strain. So it can be linear also, it can be non-linear also. Fine. So this thing is done. Next thing is regarding the hoop stresses. So this is the second concept. What is hoop stresses here? The hoop stresses are basically the pressure which is exerted due to pipes or pressure vessels on the inside. So this pressure is basically called as your hoop stress, or this pressure which is generated on the inside wall of pressure vessels or pipes is basically called as hoop stresses. Okay. So systematic engineering approach to determine the internal forces and deformations is being inculcated here. So again, basic things are you need to know what is basically tangential force being implemented. You should know how the derivation was being implemented. You should know what is the value of Ft, what is the value of Fr, how it is calculated, and so on. Okay. So basically, the first thing is regarding the force equilibrium and the free body diagram. You need to first calculate that. Now it is just these are just the points by how the professor has implied or basically derived the things regarding the hoop stresses. I am just going by them as quickly as possible. So basically by analyzing the radial forces Fr, it is concluded that for the hoop to maintain its shape, the net radial force must be 0. Therefore this complete value of Fr on the net for the complete surface should be equal to 0. Okay, the net radial force must be equal to 0. And similarly, if a non-zero radial force is existed, so just as a concept, this has been written here. But if a non-zero radial force is existing, a hoop would deform into a non-circular asymmetrical shape which contradicts real-world observations of pipe behavior under fluid pressure. That means simply as in if you actually find a circle which is actually converting, not a circle, basically a pressure vessel or a pipe which is actually exerted upon with some of the pressure, you will not find anything which actually gets deformed shape in real life. That is only the basic concept of the last line which has been explained here. Okay. Now moving to the derivation of tangential force, which is nothing but the hoop force. So the internal pressure P creates a tensile force along the circumference of the hoop. Okay, along the circumference of the hoop. How to calculate it? Using just simple integration, or basically the second method which the sir explained, which was regarding the projection method. Okay, so by considering a small angular element delta theta, the value of the radial force is calculated as delta Fp is nothing but equal to P into B into R into delta theta. Okay, so for the derivation you can just simply go through the lectures. I'm just going through a quick revision. So delta Fp is nothing but equal to P into B into R into delta theta. Okay, what is B here? B is the width. What is R here? R is the internal radius. Okay, fine. Similarly, for the tangential force, what we can do? We can find out this is nothing but equal to Ft is equal to P into B into R. Okay, fine. Next is the same thing but using the projection area method. So an alternative or a more intuitive method is to calculate the force acting on the projected area of the hoop, a rectangle of dimensions. Basically, if you cut this and basically find the projection of this is nothing but a rectangle up here, right? So this method yields the same result, that is P into R into B, right? So B will be completely the thickness around, and what is the R? R is the projected length of the rectangle. Okay, and is a shortcut in engineering analysis. So one of the reason of inculcating this concept of project area method is that there are several different analogies which can be created in the future or in subsequent different subjects in which projected area method can be used to actually calculate, let's say, for here it was force. In some another way it can be used to calculate flux in some electrical engineering concept and so on. So that was the main reason of basically explaining what is projected area method up here. Fine. So that was regarding the hoop stresses. Let's move on to the third point, that is regarding the deformation analysis. In deformation analysis, what was being explained? The circular hoop can also be modeled as a flattened rectangular plate to calculate its deformation using the Hooke's law, that is delta is nothing but equal to PL upon AE, right? What is the geometric transformation? By unrolling the hoop, the length L becomes the circumference. Therefore, approximately it is 2 pi into r plus t by 2. Okay, so therefore, how to calculate delta t? Delta t can be calculated as nothing but equal to 2 pi p r square upon small t into capital E into 1 plus t by 2r. Okay, so what is t here? T is the thickness inside. Okay, what is p here? P is the pressure. What is r? R is the radius of the pipe or the pressure vessel we are working on. Okay. Axial elongation, so treating the hoop as an uniaxial member of cross-sectional area A, area A is nothing but equal to B into T, T is the thickness inside. The resulting axial elongation delta T is derived based on the tangential force Ft, modulus the elasticity E and geometric dimensions. Okay, so this is the similar way in which the axial elongation can be calculated. Okay, so this was the next lecture which was regarding the hoop stresses. The last, one more thing is remaining, a radial expansion. So radial expansion is nothing but, so as we calculated the tangential expansion, similarly we can calculate a radial expansion. How the radial expansion is calculated? The radial expansion is nothing but the total thickness. So basically, if we actually use it, you understand using the concept of projected area, the increase in delta t can directly be linked to the increase in the radial expansion. Okay, so basically we can directly use delta r nothing but delta t by 2 pi. So we are basically dividing it into infinitesimal divisions. So t is equal to 2 pi r. In similar fashion, delta r is equal to delta t by 2 pi. Okay, therefore, we can get delta r is nothing but equal to P r square upon T into 1 plus T by 2r. Now, if T by 2r can be neglected, then we get delta r is nothing but equal to P r square by small t into capital. Okay. One of the reason or one of the most important thing which we need to remember here is that width of the hoop D does not influence this expansion. So, radial expansion is independent of the thickness or the width of the hoop. Okay. Fine. So, that was regarding the radial expansion of thin wall pressure vessels. Moving forward, next is regarding the mechanism of a belt around a wheel. So this is nothing but a concept in which is being actually used in brakes. The best example is for brakes. So basically, you apply a brake. So what actually happens for the gears, how the thing stops, and so on. The derivation has been explained by the professor. I am just going through the revision. So finally, I'll just go around it. So the mechanism of a belt around a wheel. So this section addresses the design of brake bands or belts used to stop rotating wheels where friction at the interface is critical. Okay, unlike frictionless pulleys where tension is constant, friction causes a causes a difference in tension between the two sides of the block. What is the tension being talked about here? The one tension is basically regarding this portion, and the second tension is regarding this portion. Okay, but here we don't need to actually calculate regarding 2 points. We need to calculate the actual friction which is being exerted upon the complete brake pad. Okay, so that is the main concern. Okay, there are two tensions, but the major thing is here regarding the friction, which is being exerted in the complete region. Okay, so the friction causes a difference in the tension between the two sides of the belt. Okay, so this is one of the side, this is the second side. Okay, by analyzing a small element of the belt and establishing the force equilibrium in radial and tangential directions, the relationship between the tensions T1 and T2 can be derived as T2 is nothing but equal to T1 into T1 to the T1 e to the power f alpha, where what is f? F is the coefficient of friction, and what is alpha? Alpha is the angle of contact. Okay, so here alpha can be actually conveyed as 180 degrees. Sometimes the angle of contact can also be 90 degrees. It can be sometimes 270 degrees also. So the question, please look at the question very carefully when you are solving braking forces or basically mechanism of belt around the wheel questions. Okay, angle plays a very crucial discussion point here. Okay, so tension is shown to increase exponentially as the belt wraps around the wheel. This is a fundamental concept for designing effective braking mechanisms. Okay, so that was the basic concept regarding the mechanism of belt around a wheel, hoop stresses, and the force displacement relationship. Okay, so that thing being said, let us wind up the division and let's start doing some problems. Okay, so we'll start with a few very simple questions and then we can move forward with hoop stresses and the mechanism of belt around a wheel question. Okay, so please try solving this. This is a very simple question, only resolving of forces, and please give me what is the answer regarding this. I think there are three easy questions which are somewhat related to your assignments, and then we can start using some complex questions. Okay, so please solve this and tell me what is the answer for this. Anyone with the answer? So first of all, we will be creating just the free body diagram for this. So as you can see that the P force is acting up here, right? So we can just resolve it into components. And similarly, the weight is being acted up here, which you can resolve into components again like this. Okay. So basically, now the question asks is determine the horizontal force P to be applied to a block of weight 1500 newtons to hold it in position on a smooth inclined plane. As it is written, it is a smooth inclined plane, therefore no force is being acted up here, which makes an angle of 30 degree with the horizontal as shown in the figure. Okay, so you will just need to calculate this and you can get the answer. So what you can do is you can just use summation fx at this side. Okay, so this is nothing but you can use p cos 30 and w sin 30. Okay, so I can just simply write this as this is nothing but p cos of 30 degree and this is nothing but w sin of 30 degree. Okay, so when you will use summation fx equal to 0, let us suppose that this is your x direction, this is your y direction. So p cos 30 degree is nothing but equal to w sin 30 degree, and when you will solve this you will get the answer of b as nothing but equal to approximately 866 newtons. Okay, as simple as that. Only use of equilibrium, some equilibrium for equations and fbts. Okay, fine. This is the second question. Please try this question. Please, I suggest you please try. That is the best way in which you can utilize these 2 hours. So please try to solve this question. At least try to make the FBD. Try to see the direction of force, frictional force if you're making it correct. Okay, please at least try to solve the question, at least try to solve half and give me something. Okay, so this is the second question. There are two blocks A and B connected by a horizontal rod and frictionless hinges. Please look at this. Oh, sorry. So frictionless hinges are given. So basically, this is a friction. The frictionless hinges are being exerted upon here, supported on two rough planes as shown in the figure. The coefficients of frictions are 0.33 between block A and the horizontal force. Here the frictional force is 0.33, frictional coefficient, sorry, and 0.42 between block B and the inclined surface. Here it's 0.42. So if block B weighs 300 newtons, what is the smallest weight of block A that will hold the system in equilibrium? So you just need to calculate the value of W of A. Okay. So please try to actually at least make the FBDs. Please try to actually find out what is the tension force and give me the answer. So this is the typical FBD of block B. Okay, at least from the made up FBD, can you at least give me what will be the direction of frictional force up here? Will it be up or will it be below? What is the stipulated direction of block B? Is it down? Is it up? If it is down, then will it go up? Or if it is going up, will it go down? Please at least write this. Please at least make this class a little bit interactive so that I can know if you are understanding the problems. Please write. You can write in chat. Okay, F is upward. And what is the direction of movement of block A? Is it left or right? Okay, fine. So basically, what is actually happening here? In simple terms, the major force which is acting upon this is the gravity. The force is trying to pull it down. If it's trying to pull it down, the resisting force will be in the upward direction. Therefore, if something is trying to pull it down in like in this direction, the friction force will be in upward direction. And because it is trying to pull it down in some way or the another, if you try to analyze it, it is going on the left hand side direction. Okay, so that is why we will put the value of F is in the upward direction. These are the only things in which people make mistakes. So I'm trying to explain these small concepts only. Mathematics and explanation of equilibriums are now the easiest parts. You need to understand just the direction of the forces and so on. Okay, fine. So it's nice so that you can correctly explain the direction of force. Okay, so now in nothing remains. You just need to use summation fx equal to 0, summation fy equal to 0, and you can get the answer. Okay, so let's say if I resolve all the forces along the inclined plane, so you can get how to write it. I shall write it here. So it's nothing but your force F is nothing but equal to due to mu a wa, that is the force which is coming from the block A, and second is regarding the weight. Okay, so we can just simply write this as nothing but equal to uh, this is 0.33, mu is 0.33 given to you. We need to just calculate what is the value of wa, correct? And this is here in opposite direction, correct? Because it means inside either you can write sine 30 or you can write cos 60. Okay, so this is nothing but just simple mathematics I'm doing, right? And similarly, if you do it along the plane, so first was regarding this direction, I did regarding this direction. Now let us suppose I do regarding this direction, then we can get uh, let's say this is the normal force, which is nothing but equal to right. So now if you correctly use equation 1 and 2, you can simply get the value of wa is nothing but equal to 673 meters. Okay, approximately 673 meters. Okay, so these are the basic problems regarding friction, okay, and resolving of forces. Okay, fine. So that thing being done, let's move to the next problem. Okay, so now this involves your concepts of displacements and so on. Okay, so this is a very simple question. Please try to solve this, and then we can move forward. At least try to give me second question is okay. Try to give me the answer for the first one. It's a very simple question. Please try to calculate and give the answer for the first one. Anyone with the answer? You just need to use F is equal to K delta and moment equation. That's it. Please give me the answer for the first question, first part of this question. As there's a hinge, you just need to use the moment equilibrium about the point and directly use F is equal to K delta. Please give me the answer for the first part of this question. Yeah, correct. So simple question. The weight is being exerted upon here. If the weight is being exerted upon here, then the spring will be compressed, and if the spring will be compressed, it will exert an upward force. Okay. So if it is exerting an upward force, you just need to calculate the force, which is here F. Let me write that as nothing but equal to K times delta. Okay, and this is the hinge up here. Okay. So let us calculate the moment regarding this. Let's not write M, then it will create confusion. Let us write this as point A. Okay, so let us just do simply summation MA is nothing but equal to 0. Now it's nothing but FW into this complete length is 1.35 plus 1.5. So it's 1.35 plus 1.5 is nothing but equal to the force, which is nothing but K times delta into multiplied by 1.5. Okay, now everything is given to you. I think K is also given. K is nothing but 35 kilonewton per meter. Okay, W is given to you as 600 newtons. Okay, you just need to calculate this, modify this into newtons. It's 35,000 newtons per meter. Now if you calculate delta, then you will get the value as nothing but equal to 0.03257 meter. Okay, so that is how we can calculate the value of delta. Okay, so this was the regarding the first question. Now the second question says that determine if making a diving board perfectly rigid would change the amount the spring deflects. So they are basically trying to make it rigid. Okay. So please think regarding the second question. So will there be difference in the value of delta, or will there be no difference? So any part of our question was dependent upon the deflection or some self gravity or something related to the bar. So no difference. Yeah. So basically, because the complete concept was regarding only usage of summation equilibrium equations, that's why there is no difference in the value of delta being calculated. So either you do it by rigid or use a deformable body, there won't be making any difference because we are just simply using a hinge force which is exerted at the at certain point and the value of W. Okay, if it would have been a statically indeterminate problem, then there would have been something related to something being rigid or something being deformable. Okay, so that is some different case. But as far as this question is considered, there is no change in the value of deformation. Okay, fine. So that was regarding the simple question regarding use of this F delta K delta and summation moment equations. Okay, let's move forward. Okay, again a simple problem. Please try to solve this. Just it's just the analogy part in which, as far as you can understand, what is the value of deformation being considered, what is the value of area being used to calculate internal pressure. Okay, so those are the main things required up here. So the question is simply a pressure system is equipped with a safety valve featuring a 50 diameter discharge hole. So as you can see, it's a discharge hole is being explained up here. The spring holding the valve closed has an uncompressed or free length of 250 Okay, and a stiffness constant is given to you, that is 120 kilonewton per meter. Based on the provided diagram, the spring is compressed to a length of 207 So from this, you can actually calculate the value of delta. Finally, you just need to calculate the value of internal pressure to push the valve open. Okay, so please try to calculate this. Again, just simple use of K delta and simple definition of pressure. Okay, so please try to solve this question. Again, just simple maths and simple usage of K delta. Please try to solve this and give me the answer for Fs, or basically the internal pressure. Okay, so the question is simple. The free length was given to you as 250 mm for the spring, and it is being compressed to 207 mm. Okay, so what is the force being generated up here? The force generated here is due to the compression of the spring. Okay, so the compression of the spring leads to exerting of the force outwards, and that exertion of the force outwards leads to the internal pressure. Okay, so we'll just use simple equation. First of all, what is delta? Delta is nothing but equal to 250 minus 207. So it gives you the value as 43 mm. 43 mm can also be written as 0.043 meters, right? So next is using the calculator of force. Force can be calculated as nothing but F is equal to K times delta. Okay, what is the value of K? K is nothing but 120 kilonewton per meter into 0.043. Okay, which is nothing but equal to 5160 newtons. Okay, now I can write as the upward force exerted by the pressure. Okay, pressure as in exerted for as in the pressure which is being actually accumulated up here is nothing but equal to a downward spring force. Downward spring force. Okay, so therefore we can get that pressure P is nothing but equal to force upon area, and here this is nothing but 5160 divided by pi by 4 into some radius d, or d. Now just give me what should be the value of d. Okay, simple question only. What is the value of d up here? So this d is nothing but equal to 50 mm. Okay, because we are actually calculating regarding the internal pressure, so we have nothing to do with this outward point. Okay, so when you just calculate it, you will get the answer as 2.63 MPa. Fine, nice. So that's how you can get this value. Again, a simple question. We just need to use the value of F is equal to K delta, and finally just utilize it to calculate the pressure. Fine. Okay, sorry. So I just explained this, that you just need to use the value of F is equal to K delta, and using F is equal to K delta, and finally for pressure you just need to keep in mind that the value of A being utilized up here is nothing but for your internal device, that is 50 mm. So we have nothing to do with 400 mm, because the question asked is regarding the internal pressure, not the pressure which is being exerted outwards. Okay, so that was the main thing to be understood here. Again, a simple question, we just need to use F is equal to K delta and pressure P is equal to F by. Okay, nothing, not even equilibrium equations is being used up here. Fine. Okay, now let's look at one of the compatibility question. So this is the next question, in which there are three springs, as you can see up here. These three springs, of which A and B are having same value of K, and the C is having different value of K. But this has to be in equilibrium such that the value, this small baffle is actually horizontal. Okay. So the question asked up here is, you need to calculate the mounting distance from the center for the spring C so that the sound baffle hangs perfectly level. Okay. So the diameter is given to you, the weight is given to you. You need the value of spring constant for A and B is given to you as 14 kilonewton per meter, and their distance from the center is also given to you. Okay, so this distance is also given to you from the center. This is the center. You just need to calculate this value of, let's say, R, or let's say XC. Okay, so please try to calculate this. Again, a simple question, just used compatibility. Compatibility is in, compatibility is nothing but your general logic. Okay, you just need to understand, okay, some delta is going above, then there might be some another delta which is going down. Or let's say if something has to be kept in equilibrium in some distance flat, then if the amount of delta exerted by A is something, let's say K, then the amount of delta exerted by C should also be K. Okay, so these are the simple logics which you need to use. Okay, so this is the fifth problem. Try to solve this once, then we'll move forward. This question can also be solved using the concepts of center of mass analogy. So even you can understand it. Consider the complete x-axis along the C spring, as in consider this to be your x direction and others to be this to be your y direction, and then try to understand again. I'll make it much more simple sense. So you can assume this to be your x direction. That will make the problem much more simpler, and this to be your y direction. Okay. Yeah, sure. Yeah, sure. Yeah, yeah. You can use summation of moment at the center because it is in equilibrium. So each of the points at the baffle is actually in equilibrium. So the moment of summation of moment at any of the point is equal to 0. So what is the value of delta, the deflection you are getting, or else the value of forces you are getting? Delta is 0.018 meter. Check once. Hmm, there is some calculation mistake, I guess. So try for 2 minutes more. Please check the delta. Delta should be same for each of them. Okay. Just the value of spring constant is same for two of them, and third it is different. And the complete summation of forces is nothing but due to the weight. So weight is basically pulling it down, and the exertion of force is basically pulling it up. Yeah. Okay. So here W is nothing but equal to K times delta plus KB times delta plus uh, should be KB. kb times delta plus kc times delta. Okay, so if we'll just calculate it like this, we can get the value of delta is nothing but equal to, what is the value of W? That is nothing but 1.1 kilonewton divided by 14 plus 14 plus 16. Okay, therefore the value of delta is nothing but equal to 0.025 meters. Okay, therefore we can get the value of therefore we can get the value of Fa is nothing but equal to Ka times delta. Therefore that is nothing but equal to 0.35 kilonewtons. Okay, just using the value of F is equal to K delta. Similarly, we can get Fb is nothing but equal to 0.35 kilonewtons again. And for Fc, a little bit increase in the value because Kc is different, that is 16 kilonewton per meter. Hence, it is nothing but 0.40 kilonewtons. Okay. Now the question asked is that um, determine the mounting distance from the center for spring C so that the sound baffle hangs perfectly level. Okay, now if you will just actually calculate the summation of moments along the C, along assuming the H direction to be in along the C direction and other directions to be in what ways 120 degree or let's say 240 degree apart from each other. Okay, so try to calculate the moment from this point. Okay, so the moment which is nothing but due to which is exerted due to the spring C is nothing but at a distance of R, or let's say the mounting distance or XC, which we need to calculate, correct? So the moment due to weight is negligible, means is not present because we are actually standing or we are actually calculating the moment from the center point. Okay, so the complete moments will be nothing but the summation of all the summation of forces from all three different directions. But the point is, just the point is that we need to calculate it along the length, which is x direction up here. Okay, that x is nothing but on some different perspective because it's not directly 1 meter from here, 1 meter from here. It's actually cos of that distance. Try to understand this. This is the only main concern up here. That is, we cannot actually use 1 meter here because that is not from the actual momentarily distance which we need to calculate. That value is nothing but cos of 120 degree and cos of 240 degree, or let's say minus cos of 120 degree in another sense. Okay, so therefore when we actually calculate the summation is nothing but equal to Fa into Xa plus Fb into Xb plus Fc into Xc, which is equal to 0. Okay, and here Xa will be nothing but equal to where is A? So this is nothing but equal to cos of 120 degrees, and this is cos of 240 degrees. Xc we need to calculate directly because it's along the length of x direction. Okay, so please try to understand this. Please try to understand visually also how this is happening, why it's cos of 120 degree means 1 into cos of 120 degree because the length is 1 meter up here. Okay, nothing remains. When you just input the values of Fa, Fb and Fc into this equation, you can simply get the value of Xc, which is nothing but 0.875. Okay, so this is not a 2D case, this is a sort of a 3D case, so you need to understand the concept in 3D view. Okay, so that's how you can get the mounting distance on the center of the string so that the sound baffle actually hangs perfectly level. Fine. Okay, now let's move on to the next question. That is a little bit of theoretical question. The question says that an operator uses a foot level to control a portion of a punch press machine. So this is an example of a punch press machine. The lever is equipped with a return spring that pulls the lever back to its resting position after it is pressed. Okay, the operator is experiencing fatigue from repeatedly pushing the lever downwards. So his work is to repeatedly push it up and down, up and down, up and down. Okay, suggest a modification to the spring so that we could make the lever less physically demanding for the worker. Okay, so just to explain what is actually happening here, again a simple cause. Just look at the system up here. If you look at the system accurately, a force is being a force has been exerted by this person, and there is exertion of the force in the opposite direction. So in all way or the another, we just need to focus on the spring up here. Okay. So if you will just do simple summation of moments, we will get, let's say if you are actually doing summation of moment, is what's the right? Shall I write it as foot? F foot into D foot is nothing but equal to F spring. Let's say we are actually calculating the moment from the hinge portion of here, okay, into that D spring, okay, whatever the distance may be, okay. Now, if we will actually need to focus on F foot, this is nothing but equal to, in the place of S spring, we can write K times delta into D spring by D foot, okay. Now, looking at this equation, just suggest me what shall we do so that the amount of force is being reduced. Okay, a very simple theoretical question, you just need to understand. So can we change D spring? Can we change D foot? Can we change delta? Or can we change K? And should we increase something or should we decrease something? Yeah. So it's basic. So basically, what is our aim? Our aim is to make the operator, the worker which is trying to push and pull the lever, to be less demanding. The work should be less demanding for him. So in all sense or another, we just want that the value of F foot should be lowered. Now, if the value of F foot should be lowered, we cannot actually reduce the deflection up here, because that amount of deflection is actually required so that the punching machine may work. Okay. The D spring and D foot are actually constant. So the only thing which is remaining is K. Okay, so basically what we need to use, we need to just use a spring with less spring constant. Fine. So that is how this question can be answered. Okay. These questions means made many more, much more questions regarding the theoretical concept can be made. So that's why I have added one of the question up here. Sometimes the question can be complex, such that let's say this is just a single spring. I can add two more springs up here. Or let's say one pulley is being attached here, or let's say some force is being applied up here. Then the question may be asked again that if we need to actually reduce the amount of force, what shall we do? Again, the concept remains same. You just need to look at the system up here, try to calculate all the forces, calculate all the moments up there, and try to find out how to reduce or increase. If the question is asked regarding increase, then the question will be different. But generally, it is regarding a reduction in the forces. So that our, as a person, we need to reduce the forces or the work we require. Okay. So that's how the questions can be framed. More complex questions can be framed regarding this. Fine. Okay, now let's look at example which involves rigid horizontal member also, and deformable members also. Okay, you just need to keep in mind that the deformable members can have some value of delta or deflection. Rigid members cannot. So their actual position before application of force and after application of force remains the same. Okay, so try to solve these questions. This seventh and eighth are very interesting questions. Try to solve them as detailed as possible. I will give you time, but actually try to give something to me so that I can understand that you have understood trusses, you have understood summation of forces, you have understood the equilibrium equations, and you have understood now the deflection part also. Okay, so try to solve this question. At least take some time, take 10 minutes, take 5 to 10 minutes, and try to solve this question and give me. So what is the question asked? Calculate the estimate the angle. Okay, let's not go to the estimation of angle directly. Even if you give me the value of delta A, or let's say give me the value of force in AC, we can actually understand and then we can move forward. Okay, so at least try to solve this. At least try to make the FBD for this and try to understand what is happening here. So this 7th and 8 are very interesting problems. I would suggest at least try to solve these questions by your own. So what are the forces in FBC, FCD, FBD, FAC? Okay, so if you look at the diagram carefully, there is no external horizontal force being acted up here. If there is no external force which is acted in the horizontal direction, let's say if we calculate the value of uh, the summation of forces at this point, there will be some force in this direction. Let's say this is Fy, and there will be some force in this direction which is Fx. Okay, Fx is nothing but 0, correct? This Fy will be equilibrated with this value of FBD, correct? But there is no force in this direction, therefore we got FCD is nothing but equal to 0. Okay, similarly in this point, for this point, if we actually calculate again, rigid will not have anything to do with forces up here. Okay, what is the value of FBC? FBC is in this direction. Now if you will actually take the component of this in this direction and actually sum it with summation something outside value which is 0, this is nothing but FBC, and if we will do summation Fx equal to 0 up here, we can again get FBC is nothing but equal to 0. The force in FBC is 0. If it is deflecting, if it is having some value of delta or not, that we will look afterwards. Okay. Okay. So now let us calculate the moment from this point. You can either calculate from A, you can either calculate from B. It's your choice. Let's start with the summation of moment about point A. So summation of moment about point A will lead to only two different forces. One is regarding this P and one is regarding this reaction force at D. Correct? So therefore what we'll get simply P into this 5 fits is nothing but equal to force. Now this reaction force is nothing but equal to the FBD force, okay, in opposite sense, okay. So in one way or another, either we can do it in this fashion or either we can do it in this fashion also. We can directly cut it using method of sections up here, and you can actually look at this system, okay. So if you will actually look at this system up here, let's reduce the number of steps which we are performing, because finally we only need FBD up here for first of all. So it's FBD into 6. Okay, so P is in this direction, FBD in opposite direction, therefore FBD is in compressive. Okay, so this is nothing but FBD is nothing but equal to 20,000 into 5 by 6, which is nothing but equal to 16,666.67. Fine. Now similarly for the complete system, we can actually calculate the value, or for the same system we can actually calculate the value of FAC. okay, using again the method of sections, okay, because even after cutting the method of section by the slicing, yeah. So FAC is nothing but, similarly we can calculate FAC. FAC is nothing but equal to 20,000 minus uh, this 16,666.67. Okay, so therefore we can actually get FAC is nothing but equal to 3,333.33 lbs. Okay, the thing which we need to understand here or remember here is regarding whether the force direction we are implementing is correct. Okay, because people make mistakes up here only. Either they will consider it to be tension, because sometime what will happen, let's say if I actually calculate up here, but the amount of force is in opposite direction for FBD, they will reverse the sign, and if they will reverse the sign, the complete analogy, complete discussion will be or some complete calculation will be wrong. Okay, so therefore please, whenever you try to calculate everything, try to understand the forces, try to understand the compression or tension very carefully. Okay, fine. So therefore now we have the value of FBD, now we have the value of FAC. Okay, now if you have those values, you can actually calculate deflections at the points A and B. The deflections of the point A and B is nothing but due to the deflections of this AC and BD. Okay, so now using simply the equation, delta A is nothing but equal to force FL upon AE, right? So we know what is the value of F. F is nothing but FAC, correct? So FAC is nothing but 3,333.33 pounds. Length will be nothing but 4 fits multiplied by 12. Why 12? Because the value of area is given to use in inches square. Okay, so I will just keep on writing also. And one thing more, for your exams or for future references also, try to understand this SI units also. Okay, sorry, this units also, right? You should know what is the conversion of feet to inches. You should know what is the value of G in inches, G in LB per in PSIs. Okay, we should know what is the value of Young's modulus in PSI. Okay, just not regarding SI unit. You should remember for uh, this units also. So it's 333.33 pounds into what is the length? Length value is given to you as 4. So it is nothing but 4 multiplied by 12, which is in inches, upon what is the value of area? Area is 15 multiplied by E. E is given to you in assumption as 30 Wentworth checks. Okay. So when you will calculate the value of delta A is nothing but equal to your 0.0000356 inches. So that is the value of deflection of A in the vertical direction. Similarly, you can get the value of delta B. Again, delta B, I will just write it directly. Delta B is nothing but equal to 0.002667 inches. Okay, now try to understand this. Delta A has reduced much more as compared to delta B. Correct? Sorry, delta B has reduced much more as compared to delta A. Okay, so delta A has reduced less, delta B has reduced more. Now using this, and because you know that the rigid body will not have any deformation, there will be a little tilt in the railway, in the urban railway, correct? There will be a little tilt, and that tilt is only the angle which is being required up here. Okay, so how to calculate tilt? That will be nothing but there will be some delta B up here, there will be some delta A up here. Okay, we need to calculate this distance. Let me make it directly. That is much more easier to make you understand. Uh, okay, so what is actually happening here? Delta A. So let us suppose that this is the initial. Try to understand all these concepts very carefully, because when the complex questions regarding deformations, when we actually understand all these concepts after understanding indeterminacy, deflection, stresses, all the equations, these simple things are very important, so that you can actually understand visually that what is the deflection happening, what is actually how the rigid member is bending. When bending will be added to it, when torque will be added to it, then the question becomes complex. Okay, so try to understand at least the easier questions carefully. Okay, so let us suppose that this was the original position of the this urban railway, or the rigid support, rigid member being given up here. So as delta A is less and delta B is more, what is actually happening? This is actually being tilted up in this direction. Let me just use this here. It is somewhat in this direction, correct? Like this. Okay. So let us suppose that this is the original position up here. Then this uh, this distance is actually from center to center is delta A, and this distance is nothing but your let me write it like this, is nothing but delta B. Okay, now if you need to actually calculate the value of rotation, then you need this value, that is delta B minus delta A, correct? And if you are actually calculating for infinitesimal position, we just need the value of L, because we know that in radians form we can actually calculate it using theta is equal to L is equal to r theta. Okay, so if you simply use length of this is nothing but equal to r theta, we can get the value of theta is nothing but equal to delta B minus delta A upon, I mean, not in this fashion, theta is nothing but equal to this distance, the deflection distance upon the length. Okay, therefore when you will solve this, you will get the answer as 3.21 into 10 to the power minus 5 radians. Okay, if you need this value in degrees, you can just multiply it by 180 by pi, and therefore you can get the value as nothing but 0.00184 degrees. So you can actually see this is one of a real life example only, in which you can actually see what is the value of theta actually being happening. So 0.00184 is actually very very small. It's not even 1 degree. It's not even half degree. Okay, so you can understand. But yes, the deflection exists up there. Okay, fine. So this was regarding this question. So now let us try to solve this question. Again, a very good question. Please try to solve this question. At least try to calculate the internal forces in the diagonal bar PT. Okay. Again, a concept using delta FL upon AE and so on. Okay. So try to solve this question and give me the answers for this. Please, I suggest you please solve this question, because these questions will only increase the analytical skills required for the future concepts. These questions are very very simple, because there is no bending involved here, there is no torsion involved here, there is no moment being acted up here. Okay, these are very very simple questions. When the complexity is being added upon, then the confusion creates. So at least try to solve these questions as far as you can. So what is the internal force in the diagonal member BD, diagonal bar BD? Yeah, so it's zero because there is no external horizontal force being acted upon. So if we actually calculate the summation of forces along the x direction at point B, then we can directly get FBD is equal to 0. So that was the first question. The second question simply asks that determine the horizontal and the vertical movement, that is deflection of the point A, keeping in mind that the bar AB is rigid. Okay, so please try to solve this. Actually, at least try to solve the value of deltas at E and B. Actually, at least give me the values of what is the deflection of point E and what is the deflection of point B, and in which direction. The direction is very very important as far as this question is considered. Okay, so please try to give solve and actually give me what is the value of delta E and delta B. Yes, it's correct. So it's 0.018 inches in downward direction. Similarly, calculate delta B also. So for the second question, first of all, we need to calculate the value of internal members. So for calculation of internal members, let us calculate the moment about point B. As it is in equilibrium, the summation of about point B should be equal to 0. So now the only forces which are existing up here is one is the 5,000 pounds and another is the force in the member ED. Again, I am trying to use method of sections where I am actually cutting it along this direction. Therefore, the value is so we'll just do it. 5000 into 18 is nothing but equal to f ed into 6. Therefore fed is nothing but equal to 15,000 pounds in compression. That is very important. It's in compression. Okay. Similarly, if FED is known from the complete system, if we will actually do summation Fi equal to 0, so a complete system, FED plus FBC is equal to 5000, and therefore FBC is nothing but equal to 5000 minus 15,000. Therefore, it's minus of 10,000. I'm assuming it to be in compression, but because it is minus 10,000, so in another way I can write this 10,000 in tension. Okay, so it's 10,000 pounds in tension. Fine. Now just use the value of delta E. What is delta E? Delta is nothing but equal to FL upon AE. Everything is given to you. Now if you will actually calculate it, you will get this value is nothing but 0.018 inches in downward direction. And similarly, if you actually calculate delta B, again everything is given to you. FL upon AE, you will get this value as 0.024 inches. Okay. Now try to actually visualize the complete situation. Okay. Let me first add one page up here. Okay. So here delta E is 0.018 downwards and delta B is actually upwards. Okay, so what does it mean? It basically means that if this was the initial position, then how is it shifted? It is shifted somewhat in this direction. How shall I make it? It is somewhat shifted in this direction. This is how it should look like. We actually calculated this value as delta B, and it's not up to scale. I mean, let me just make it much more better scale wise. It's somewhat like this, and this is your delta E. Okay, so that's how you need to understand this. Okay, now if delta E is known to us, delta B is known to us, then using simple equation of delta is equal to r theta, we can get delta B. Now you need to understand that the complete deflection or rotation has to be calculated for this complete triangle, correct? I will just use different triangle up here. As we used delta is equal to r theta in the previous question, similarly we are using delta is equal to r theta in this question also to calculate the rotation. But this time the value of delta will be added up, not subtracted, because they are in different directions. Okay, so sometimes some of the questions requires a little bit of logic also. So delta B plus delta E is nothing but equal to r theta. Delta B is known to us, delta E is known to us. So this is basically mod. Okay, I am actually calculating the values as mod. So don't understand this as direct. We will implement this as plus and this as minus. Okay, that's why I have actually implemented and explained you using a diagram of here. Okay, so therefore theta is nothing but equal to 0.042 upon what is the length? I think the length is 6 feet. So it's 6 into 12. So therefore theta will give you the value as 0.042 upon 72. No need to reduce it correctly. We can actually reduce it afterwards. Okay. Now similarly, for the outwards part, as in we need to calculate this value of y. Okay, now if you look at this very carefully, again we can use a simple concept, but this time y and delta e are in same line. Okay, so to calculate the value of theta, what we will do, we can actually subtract this. So it's y minus delta e is nothing but r theta. Okay, theta is known to us. Okay, so what is the value of y? Y can be calculated using this. Delta E is known to us, R is known to us, theta we have calculated just currently. It is nothing but 0.102 inches. Where? In downward direction. Okay, so that's how you can calculate the vertical deflection. Okay, I hope this thing is clear. Okay, sometimes you can use sign conventions also, sometimes you can use logic also. So I try to use a bit of logic, and the equation delta is equal to r theta. Okay, fine. R theta, but remember that this is only used when theta is in radians. Okay, now for x, understand the concept now very carefully. The deflection which is exerted on this point will be the same deflection which is exerted on this point also, because it is rigid. Okay, so now to actually exert that or actually calculate that, what we can do, we need to understand one thing. We need to understand that because the forces acting upon FBD is nothing, the value of the summation of the deflection at the point B must be equal to 0. So to understand that point, what we will do, we will just simply calculate what is the deflection of B in x direction for this force. Understand this. This won't be having any internal deflection or internal forces, but this can at least move depending upon how the forces are being exerting. Understand this. No internal forces, no internal deformation, but external deformation or external deflection is being acted upon up here. Okay. Therefore, we can write this as, so therefore there will be some deflection in this direction, there will be some deflection in this direction. We know that along the direction of the member, there is no deformation. Therefore, we can just sum the value of deformation along the line of member. Okay, so using this, we can simply get ub is nothing but equal to minus vb, and we know what is the value of vb, we just calculated for the deflection, right? That is nothing but this portion. Okay, so therefore we can get ub is nothing but equal to minus 0.024 inches, or in another fashion we can write this is nothing but 0.024 inches in left direction. Okay, I hope this concept is clear to you. Okay, sometimes we need to use geometric compatibility for some points, sometimes we need to use equilibrium equations, sometimes we need to use FL upon AE, sometimes we need to use logic. Okay, so that's how you need to be very particular regarding which concept to use when. Okay, so that is one of the typical examples. So the final question is complete. The question asked was regarding the determination of horizontal and vertical movement at point A. So we calculated the vertical movement as 0.102 inches in downward direction and 0.024 inches in leftward direction. Okay, so this is the eighth question. Let's move on to, I think, now hoop stresses. Yeah, so please try to solve this question. This is a typical question on hoop stresses. Try to calculate the value of tangential forces, and I think one more question is remaining regarding mechanism of bend, and then we can end this session. Okay, so please try to solve this question. This is a very simple question. Just implement the forces and you are good to go. So please give me the value of force in brass and force in steel. I think the value of E are given to you. Yeah, the value of E is given to you. Please try to solve this question and give me the answer for forces. So again, you need to know the actual derivation or basically the particular forces direction. You need to just cut the sample from one end. Let's see if we cut it along the, diagonally, and can understand the forces. Just understand the forces, create the FBD, use summation Fy equal to 0, the work is done. Okay, fine. So please try to solve this question and give me the answer. So here, if you will cut it along this diagonal, okay, there will be forces due to the brass, there will be forces due to the steel. There will be forces up here, 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 and here. Okay. So therefore, let's start. What is the value of force? We need to calculate the force, the total force. The total force is nothing but P multiplied by the internal radius. P is the internal pressure into the width. Okay. You know the value of P, that is 1.4 mega Newton per meter square. What is the value of internal radius? Internal radius is given to you as 3 mm, or I can write it as 0.003, and the width is given to you as 0.006. Correct? So you will just solve this, you will get the value as 5040 newtons. Okay. Now summation Fy equal to 0, simply you will get summation Fy equal to 0 will give you 2 into Fb plus 2 into Fs. Okay, you can even understand this analogy using the projection method also, which the professor has explained. So this is nothing but equal to 5040. Therefore, you will get Fb plus Fs is nothing but equal to 2520 newtons. Okay, how I got this? This is nothing but summation Fy. Summation Fy equal to 0 at this section. Okay, this section. Okay, fine. So this is the equation number 1. Okay, similarly using strain compatibility, now when the composite members have been created, for composite member you have to remember that strain compatibility always exists. What is the meaning of strain compatibility? The strain compatibility simply states that the strain which is being offered by one member will be equal to the strain which is offered by another member. Okay, what is the reason for this? The reason is so that there is no failure, there is no inversion as in the molding is not happening, the bond between the two materials being used in composite members are correct, or basically they're bonded upon together for a long period of time. Okay, so using strain compatibility, I can simply write epsilon A is nothing but equal to epsilon B. Now you know what is value of epsilon? Epsilon is nothing but force upon area, that is stress upon Young's modulus. Okay, Young's modulus is given to you, so you can simply write stress upon Young's modulus, that is EA is nothing but equal to sigma B upon EB. Okay, sigma is the unit. I am denoting stress by sigma. In the place of sigma, you can write force. So it is nothing but Fa upon AA into EA is nothing but equal to FB upon AB into EB. Okay, EA, EB is given to you. FA, FB is unknown to us. Area can be calculated simply using internal radius and width. Okay, so when you will just put each of the values up here, so area AA will be nothing but equal to 18 into 10 to the power minus 6. AB is nothing but 36 into 10 to the power minus 6. Okay, therefore using equation number 1 and equation number 2, two equations to unknown, you can get the value of F brass as 504 newtons and F steel as 2016. Okay, so I'm just leaving the calculation portion. The major understanding has been explained up here. Okay, so you just need to use the strain compatibility and summation of equilibrium forces. Okay, fine. So that was your ninth question. Let's look at the last final question and then we can end the session. Okay. So please try to solve this question. At least try to solve this question. You just need to use one simple formula. If you have went through the lectures, you know what is the formula being implied up here and what are the values of tensions. Okay. So please at least try to solve this question and give me the answer. So let's say if we call this as point A, if we will do just simply summation of moment about this point A to be equal to 0 at equilibrium, we can simply write the moment actually existing is 225 is nothing but equal to, so at least if you are assuming anti-clockwise as positive, then it is nothing but 225 into T2 is in opposite direction, so it's T2 minus T1 into the distance. What is the distance? Distance is nothing but 300 divided by 2, that is 150 mm. Okay, 150 can be written as 150 by 1000. Okay, so this is your first equation. The second equation can be derived using the mechanism, and therefore we know that if T2 and T1 are there, one breakage is being applied up here, and the complete equation or the force is being frictional force is exerted on the belt due to the mechanism. Therefore, the second equation can be simply T2 is nothing but equal to T1 into e to the power f theta, where f is nothing but the frictional angle, a frictional coefficient, and theta is nothing but the difference between the orientation of T2 and T1. Okay, so here what is theta? Theta is nothing but in radians is 3 pi by 2. Understand this very carefully. It's not minus 90 or 90. It's 3 pi by 2, and the friction coefficient is 0.4. If you will use these two equations, you can simply get the value of T1 as nothing but equal to, you will solve this correctly, you will get e to the power 0.6 pi minus 1, and therefore T1 is nothing but equal to 0.27 kilonewtons, and T2 is nothing but equal to 1.77 kilonewtons. Okay, so that's how you can solve this question also. Okay, so this is one of the very easy question. You just need to remember this. If someone doesn't know the formula T2 is equal to T1 into power f theta, then this question is difficult. Otherwise, this is very simple question. Okay, so that thing being said, let me stop the discussion up here only. These were the different questions regarding Hooke stresses mechanisms. I would suggest you please try to solve the questions regarding deformation, force displacement relationship by your own, because these things are very important when the complexity increases, when there are bonding problems, when there is bending moment being added, when there are axial forces added, when there are torque being added, then these questions become much more difficult, much more complex. So at least try to solve the simple basic questions where you are clear with all these things. Okay, fine. So that thing being said, let me stop the discussion. We'll meet in the next class. Okay, so thank you so much.